Optimization of yield lines in two-way slabs. This video deals with the type 6 slabs. The definition of the different types of slabs are as follows. Type 1 is a rectangular slab simply supported at the four sides. Type 2 has one fixed end. Type 3 has two fixed ends opposite to each other. Type 4 has two adjacent fixed ends. Type 5, three adjacent fixed ends. And type 6 has four fixed ends. This video will deal about the type 6. Looking at the type 6 slab and using the yield line theory, then we know that the angle of rotation are the 4 points where the slabs are supported. And when two rotation axes cross, there starts the yield line. So in this corner, the yield line starts under an angle beta 1, which I do not know, the other corner 2, and so on, beta 3 and beta 4. When those two lines intersect, when those yield lines intersect, we make the connection between the two. This is not all. There are also the yield lines on top of the slab, which is for the fixed end support. All around, you will have also a yield line. We assume that the maximum yield or the maximum bending moment on top is equal to the maximum bending moment on the bottom of the slab, which occur because of the this is a good hypothesis if we assume that the reinforcement on the top is equal to the reinforcement on the bottom of the slab, because we are working in an upper bound system and we are working at full yielding of the reinforcement steel. Then we can look at the geometrical parameters S1 to S4 and we will express the geometric characteristics in function of the beta values. This system has some restrictions. It must be a two-way slab. It means that B must be between A and 2A. It means also that S1 plus S3, of course, must be smaller than B, otherwise these two will interact with each other. You will not have a realistic yield line pattern. And S2 and S4 is equal to A. Now, we will use the cotangles formulation of a triangle, which says that the height of a triangle equals the base of the triangle divided by the summation of the cotangles of the two adjacent angles. Knowing that the cotangles of 90 degrees minus beta is equal to the tangles beta, we obtain that S1 is equal to A divided by the tangles of beta 1 plus the tangles of beta 4. Of course, S2 is equal to S1 times the tangles of beta 4. So that gives you this formula. We do now the same for S3 and for S4. Now let's look to it in a little bit closer. This yield line pattern must be realistic. So that means that this point and this point must be on the same horizontal line. If not, you do not have a realistic mechanism of slab parts rotating around each other. So this means that for all the variables, the four variables that we have from the angles of the yield line pattern, we can make the following expression. The distance Sx is equal to S1 times beta 1 and Sy is equal to S3 times beta 2. So this means because Sx must be equal to Sy, that you have a connection between beta 1 and beta 2. The same happens with S4, SV and SW. We can do the same arithmetic and we will find that this expression here. Combining those two expressions, we find the relationship between the four angles. we can now express one angle. It can be, it's not important which one. It can be beta 1, 2, 3, or 4. So I've taken beta 3 as parameter. It can be expressed in function of the other three. So instead of 4 variables, I end up with 3 variables. Now, because of symmetry, because every corner has the same leg adjacent and to form the angle beta 3, beta 2, beta 1, beta 4. So because of this complete symmetry, it is not possible that beta 1 up to beta 4 are different from each other. So they are equal because of the complete symmetry. So that means that beta is equal to beta e, and we used one parameter, y, x, but I call this here y, which is equal to tangents of beta. So now this is a problem with only one variable y. We look at the geometric characteristic S1 with this in mind. So we know now that S1 is A over 2y. S2 is, of course, now A over 2. S3 is the same as S1. And S4 is also A over 2, which is quite logic because those angles are all the same. So this must be the midline. Now, writing all the conditions again for this slab, we can now calculate the work done by the external forces Q. We divide the work done divided by the load, divided by the unity of deformation. And to do so, we look at all the triangles formed in the slab, formed by the yield lines of the slab, and we see that the total load is A times S1, but because it is triangles, the mean deflection is delta divided by 3. The same happens on the other side. It's A times S3 divided by 3. What is left are two rectangles. Total surface is B minus S1 minus S3 multiplied by A, and the mean deflection is delta over 2. By substituting the variables in this equation, we obtain following expression. The work done by the internal bending moments divided by the bending moment and divided by the unity of deflection. We obtain the following. It is the bending moment M projected to the axis of rotation. It gives you B multiplied by the angle of rotation, which is delta over S4. So it is B over S4 in total. Then we can do the same for this yield line. It's A divided by S3. The bottom one, it's B divided by S2. And the left one, it's A divided by S1. Of course, we also have the yield lines at the supports, which is B divided by S4, A divided by S3, B divided by S2, and A divided by S1. Substituting the variables gives you this expression, or when E is equal to D, we obtain M, and M is then a function of alpha and Y, Y, the tangents of beta 1, and it has an expression like it is written here. Of course, we have to check always if this yield line pattern is realistic. So we check this quality and we find that it's okay. So the general function of the bending moment for type 6 slabs is of this form. And now we are going to maximize it. So we are looking at the first derivative in y to obtain y max. And you have an equation, you solve this equation and you arrive at this expression. So it's only a function of alpha. Beta max is of course the arctangents of y max, but expressed in degrees. In a graph, beta max for the range of alpha between 1 and 2 gives you this type of graph. Notice that the beta, or the angle for the 30, 45, 60 degree method, is 45 degrees, which is here on the top. So when optimizing, you have a smaller angle than the 30, 45, 60 rule. Let's give an example of a slab with B is 9 meters and A is 6, loaded with 10 kilonewton per square meter. It means that alpha is 1.5. The yield lines in full green is the yield lines with the 30, 45, 60 uh, 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 rule. And the general formula is then m, the bending moment in function of alpha and the tangents of 45 degrees, because for the green, dark green ones, it's 45 degrees. And it gives you this expression. For alpha now is equal to 1.5, 9 divided by 60, we obtain the bending moment with the 30, 45, 60 method as 10.5. The angle beta max in function of alpha, we've seen that this is this graph. Here we have alpha equals to 1.5, and we can look for the angle beta for the yield lines, which is the dotted yield line. And this is something like 40 degrees. So you can use it in the formula, or you can use the graph. So the maximum bending moment is 10.6 kilonewton per meter, because we have optimized this angle. And you see in the dotted line how those yield lines are shifted towards the center. We can now substitute in the general equation the y max and the optimized beta angle, and we obtain this closed formula for the maximum bending moment. Taking the ratio of the bending moment for the 30, 45, 60 rule divided by the optimized method, and then you will see that we will have within the range alpha from 1 to 2, that there is only a 2% difference for type 6 slabs, which is quite neglectable. We can also use a handy way by saying that the bending moment is q8 squared divided by a coefficient k. And when the optimum angle is reached, we call it k max. So this is only written by just for reformulating this equation that we had on the previous slide. And we find that the k max is equal to this expression, which is only dependent on geometric characteristics. It's in fact only dependent on the ratio largest side divided by the smallest side of the slab. Then we can look at an example. For instance, for A is 5 meters and B is 7.5. So alpha is 1.5 meters and the load is 20 kilonewton per square meter. We can look at the optimum coefficient K, which is using the formula 34 degrees, more or less. So the bending moment is 20 times A squared divided by 34. It's 14.7 kilonewton per meter. So in this way, you can very rapidly find the maximum bending.